Hello students, welcome. Many of you have requested me to put up some short tricks videos on rotational mechanics for the upcoming JEE main exam. But the whole chapter can't be done in a single shot. So I have chosen one part, that is rolling without sleeping. Rolling without sleeping, or this type of problems, there is block pulley problems where there is no relative motion between block and the pulley. Now normally let's take up this problem. So you know how to solve this problem. Here pulley has radius r, moment of inertia I, about the axis of rotation, and there are these two blocks, block M2 and block M1, and one block C actually is given that M2 is greater than M1, M2 is greater than M1, so M2 will go down and M1 will go up. So you have to find the acceleration of each block. Now the typical way of solving this problem is to consider the force equation for this block, the force equation for this block, tension here, and the torque equation, then this A equal to R alpha. You know why A equal to R alpha? Because the angular speed omega of this pulley and the speed V of the string or the block, that's the same thing, is related by this V equal to omega into R, because the circumference of the pulley having speed R omega. So there is no slipping between the point on the circumference of the pulley and the string itself. So as there is no slipping, so we can write R omega equal to V, or the V equal to R omega. Yeah, here it is. So we can write V equal to R omega. So therefore if you differentiate, you get A equal to R alpha, where A is the downward acceleration of M2 and same the upward acceleration of M1, and alpha is the angular acceleration of the pulley. Now we can totally skip this force and torque tedious problem solving method and do it in one shot by work energy theorem. So by work energy theorem, if you assume that M2 goes down by distance x, and so M1 will also go up by the same distance x. So now so after going down a distance x, M2 gains speed v, M1 also gains speed v, and the angular speed of the pulley is equal to v by r. Now let us write the work energy equation. Now in the work energy equation, the loss in potential energy is gain in kinetic energy. That's for the system, not for individual. So loss in potential energy is equal to gain in kinetic energy. That is for the entire system. So loss in potential energy, so M2 loses potential energy, M2 gx minus M1 gx equal to gain in kinetic energy. So half M2 v square plus half M1 v square, and you don't forget to include the pulley, half I omega square, that is v square by r square. Now see, it's so simple, it is. See, you just write v square equal to 2 times v square equal to 2 times M2 minus M1 gx divided by M1 plus M2 plus I by r square. So actually we have considered here that the block starts from rest. When it is released, the block, so each of the blocks starts from rest, and once this M2 goes down by x and hence this M1 will go up by x, they will gain a speed v each. So now actually nothing much is left in this, v square equal to 2ax, v square equal to 2x. If you want to be doubly sure, you can differentiate with respect to time, that is 2v dv dt happens to be equal to, or that remains 2m2 minus m1 g by m1 plus m2 plus I by r square times dx by dt. Now dx by dt is nothing but v. So this v and dx dt cancel, and this 2 and 2 cancel, and dv dt is nothing but a. So you have got the answer, that A is equal to m2 minus m1 g by m1 plus m2 plus I by r square. Let's take up another problem. Here it is. Here also is the same case, that is there is no slipping between the pulley and the string, and this pulley having radius r1, moment of inertia I1, this pulley having radius r2, moment of inertia I2. Then you can solve it by the same method. This goes down by x, this goes up by x, this gains speed v, this will, this m2 will also gain speed v once it comes down by x, this goes up by x, and the angular speed of this pulley is equal to omega 1 equal to v by r1. Angular speed of this pulley is equal to v by r2. Do you know why? Because see, if you look at this pulley, suppose if you look at this pulley, see the axis. So from the axis, the circumferential speed of the pulley will match the speed of the string. That is the whole meaning of no relative motion or no slipping, So there it is r2 omega. So this velocity is r2 omega, and this is, as there is no slipping, v is r2 omega. So now you can apply the same method here, that is loss in potential energy. Let's write that loss in potential energy. So m2 gx minus m1 gx, loss in potential energy is half m2 v square plus half m1 v square plus half I1 into v square by r1 square plus half I2 into v square by r2 square. Now you can differentiate and easily find out, you can differentiate both sides with respect to t. So you will find the acceleration, which is dv dt, that happens to be equal to m2 minus m1 g divided by m1 plus m2 plus I1 by r1 square plus I2 by r2 square. Okay, so let's take up one more problem. See, you see, this problem has come in JEE Main 2019, a homogeneous solid cylindrical rod. So now see, this it's not a block pulley problem, it's actually a homogeneous solid cylinder which is pure rolling on ground. So anyway, there is no slipping, and there is no work done by friction. That is why we could conserve and apply work energy theorem in the way we did it. So else the work done by friction would have come there. So there homogeneous solid cylinder of radius r and mass m, let's put some color to it, is pulled on cricket pitch by a horizontal force. I think cricket pitch rollers are pulled at their centers, I think so. So the force applied is F, assuming rolling without slipping, angular acceleration of the cylinder. Now here there is a confusion actually. So where is the direction of friction? And if you would solve it by the traditional way, you have to consider the acceleration of the center of mass to be A, angular acceleration is alpha, A equal to r alpha, then apply the force equation, torque equation, and then there will be 3 equations actually, but we will skip all those by applying the work energy equation. See how it is done. Now what we are doing is that, suppose the center of mass of the cylinder goes by a distance x, so therefore it starts from rest, so the velocity of the center of mass is dx dt, and the acceleration of the center of mass happens to be dv dt. Now we will directly apply work energy theorem. What is work energy theorem? Work done by net force change in kinetic energy, velocity v, angular velocity omega is equal to v by r. Why? Because this is the instantaneous axis of rotation, lowest point is in contact with ground. Okay, so let us apply work energy theorem. Fx equal to half the translational kinetic energy, half mv square plus half I omega square. What's I? Cylinder, so mr square by 2, ICM, I about cm, into v square by r square. So therefore you have f into x is equal to half plus 1/4, I think you get 3/4 mv square. Differentiate with respect to x, t rather, differentiate with respect to t, or you can do with respect to x. This a is equal to dv dx, that's also true. So f into dx dt is 3/4 m 2v into dv dt. Now dv dt is nothing but the acceleration, and this dx dt and v will cancel, there you get 2. So therefore a dv dt, a acceleration of the center of mass is 2f divided by 3m. Where has this r gone? I think there is. So yeah, actually r will not come here. It is asked that find the angular acceleration of the cylinder. Okay, that's no problem. So angular acceleration is equal to linear acceleration by r. So therefore 2f by 3mr. So 2f by 3mr, C is the correct answer. So in this way you can solve this type of problems in a short way, because in JEE main you don't have time. In this method you can solve each problem later in 1 minute. So stay tuned, we'll come up with more videos.